All right, so this is another video for conservation of energy. I filmed this in class already, but the file was corrupted or something, so I need to repost this. Um, this is one of the only times you'll see my actual full face in these lessons since there is no one else in my classroom. So maybe this will make the lesson a little bit easier, quicker as well. So, conservation of energy, what is it? Basically, it's just saying energy cannot be created or destroyed. You can just switch it from one form to another. So, theory is since the very beginning of, well, the universe, energy cannot be changed or created or destroyed. So it's been the same the whole time. You can only convert it from one to another. So you can create it from energy of this, put it into energy of something else. And think about conservation. Conservation just means to conserve something. So it's you're trying to keep it the same. So you might have heard of like a wildlife conservation. They're trying to conserve the wildlife. They're trying to keep it the same. So you can imagine a ball being thrown up into the air. We're converting between different energies. So at the bottom, it's got some speed. So it's got kinetic energy. And then as it goes up and up and up, it's converting its speed or its kinetic energy into potential until it loses, or it has the least amount of kinetic energy up top, the most potential. And then that potential again gets turned into kinetic and it moves faster and it's lower potential. So at the bottom here, we've got maximum kinetic, so the maximum speed, minimum potential, so the lowest height. And then the reverse is true up at the top. So you've just got this converting, and I said this already. So as the ball goes up, kinetic is changed into potential, and as it comes down, potential turns into kinetic. This is similar to a pendulum. I think some of you have seen this from last year. So the highest point, maximum potential. Potential energy, the highest point is the maximum, and there's no kinetic energy at this point. So it comes to a complete stop, no kinetic, before it comes down. And at the bottom, the lowest position is always the minimum potential, which gives you the maximum kinetic. So when one is the minimum, the other is the max. They just bounce back and forth as they're moving along. So the question is, if you're on a roller coaster, why is the highest point first? Not all roller coasters are like this. New ones are creating stuff that's different, so you might have something that doesn't start at the highest point. But essentially what you're getting is you want the maximum energy at the beginning, the potential, so that you get the maximum kinetic somewhere else. So you put all this energy in, you've got this track that pulls the cart all the way up to the top, and then the rest of it can just slow you down. If you're given the most potential at the beginning, it's you don't have to give it any more energy. It just converts that potential to kinetic, back to potential, to kinetic, and so on and so forth. So that only works when we're dealing with conservative forces. So gravity is conservative. Basically, conservative just means I can gain that energy back. So for instance, if I take my water bottle here, if I raise it up, I give it some potential energy, and I can lose that in the same way doing the reverse. So I can have energy, lose that energy, and gain it back. As opposed to friction, if I slide my hand this way, I'll lose energy to friction. If I slide it back, I don't gain back that friction energy anymore, which is called heat. I don't gain it back, I lose it again. So conservative just means I can gain that energy back. If we have something like friction, this is not conservative, meaning, like I said, we'll lose it. So when our ball is bouncing something like this, you'll notice it doesn't gain the same potential energy each time. That's because I'm losing energy to friction, to heat, to sound. I'm losing energy. So if you lose energy, things happen. But most of the time, we're going to deal with conservative forces. So what is conservation of energy? Well, if I'm gaining kinetic energy, I'm losing potential, and vice versa. If kinetic goes down, potential goes up. So it's this balance between these two things. So here's the expression. When I change my kinetic energy, this is equal to negative the change in potential. As one increases, the other decreases. Yep, said that. And this is our general equation. Energy initial equals energy final. I'm dealing with kinetic and potential, kinetic potential. So essentially it just says, since I cannot lose energy, it's just converted, the energy I start with is the energy I finish with. So what I start with is what I finish with. So that is this. When I take what you've learned from potential and kinetic energy, plug in those equations, you get something like this. So this is the main equation you'll see. You don't see this one as often. It's mainly just this. That's going to be the big one you do. So let's try a few questions. So if I've got something like this, what do we got? We got a person wanting to jump over the Great Wall of China from a skateboard that's on a ramp. Okay, let's give this a go. So we've got, someone's got a ramp here. They want to go over Great Wall of China. Yep, I know. My drawing is fantastic. Here we go. So here's our skateboarder. And what we are told is we need to have a specific speed down here. So here's our initial position. Here's our final. We want to know how much potential energy do I need to start with. And something you should see right off the bat, kilometers per hour. We don't want kilometers per hour. So we're going to take this, we're going to divide by 3.6. Remember, that's our magic number. And what does this give us? I have my notes open here on the screen, that's why I keep looking at it. So 21.67, right? Yep, meters per second. Because that's our units that we want to deal with. So now, looking at this, if I wanted to figure out what A is, I'm dealing with energy initial equals energy final. So the kinds I could have at the beginning would be EPI plus EKI. So initial potential, initial kinetic. What am I doing here? EPF plus EKF. So the nice thing about this, I'm starting at rest at the top. So my kinetic energy initial is 0. And if what did I draw here? I think that was supposed to be an F. And if my bottom of the ramp here is our 0 potential point, this is 0. So we're just going to say this is EP equals 0, because it's relative. I can pick what position is 0. So this is great. All I need to do to figure out what is my initial potential energy, just solve what EKF is, which is half mvf squared. I have the mass, I have the final velocity, I can solve for EPI. So this is just simply a half times, what did I say the mass is, 82, times the velocity, 21.67 squared. Don't forget the squared. Many people forget the squared. And this is 1,947. You could round this, so 19,000, that'd be fine. If I want the height, I'm just using this. EPI, which is the number I found, equals mghi, and solve for hi. You have the mass, it's 82, you have g, it's 9.8. I'm not going to do it for the sake of time, but you could solve for height there. Not too bad. Let's try this one. So now we've got a person on a trampoline. Here's our trampoline. Here's our basketball hoop. Yes, this is my totally artful skills. Okay, so he's jumping up in the air. He's got his basketball. He goes down, and then he jumps horizontal towards our hoop here. Doing a good old Michael Jordan. Okay. And what are we told? We're told that this height is 4.8. That's a 4. And we are told at this height, he's 3.2. So he's got 2 potential energies. And we want to know what is his speed at this point. So set up the exact same equation. Energy initial equals energy final. And solve it. So EPI plus EKI equals EPF plus EKF. You're going to get very familiar with these. And cancel out what we can. At the very peak of his arc, he's got 0 speed. So that stays as such. And then we can figure this out. So EPI is MGHI equals MGHF plus a half MVF squared. And we're solving for VF. Now notice I don't give you the masses, but that doesn't matter because there's a mass in every single term. So those actually cancel out. And now I can solve for VF. I know G, H initial is 4.8, 9.8, so I can plug in numbers for here. We've got 9.8 times initial height, which is 4.8, equals 9.8 times the final height, which is 3.2, plus a half VF squared. Do the math. Again, don't forget to take the square root. You get 5.6 meters per second. So that is his speed as he's flying towards the hoop. Last question. So with this one, I'm going to show you a little trick here. Remember that potential energy is relative, so I can pick whatever 0 point I want and make this work. So the trick I'm going to do for this question here is I'm going to change my potential energy to be 0 at this point. So I'm going to say at this second hill, my potential energy is going to be 0. So instead of making it from the ground so that my heights are 45 and 25, I've said my EP is now here, which means all my heights need to be relative to here. So that means this needs to be 20 meters. Since this is 25, 45 minus 25 gives you 20. From here, I can now solve this, and I can solve it a lot easier. So E energy initial equals energy final. This in and of itself gives you 1 mark. So this is worth writing down. So let's see, EPI plus EKI, I'll write this a little nicer, EKI equals EPF plus EKF. What's 0 in this case? I start from rest here, so my kinetic energy at that point is 0. I said this line is my EP equals 0, so at this point, that's 0. Now it's pretty straightforward. So I just have MGHI equals a half MVF squared. I give you the mass, but notice I could cancel it out here. It doesn't always cancel, so I'm not going to cancel it this time. And then let's go ahead and solve this. So 65 times 9.8 times the initial height, which is changed to 20, equals a half times the mass, which is 65, VF squared. So we get VF equals 20 meters per second. So that is our final velocity. And notice that's the strategy with this. So you can set your EP to be wherever you want as 0. If you set it at the ground here, you'd still get the right answer. You'd have EPF is at 25 meters, EPI is at 45, so it would still work. This just saves you a little bit of algebra. So that is conservation of energy. And notice how quick this went. How much time is it? 16 minutes. I almost feel like I should do this more often where I just teach it ahead of time. It's just twice as much work. So that is it.